In this section, we will discuss the idea of refinement and how methods help implement that. In many scientific documents, they begin with a small chunk of text called an abstract. What it does is briefly describes the idea of the paper without giving any real specific information. It should be sufficient that you get the idea of what's inside, but without any details. That allows a reader to know whether or not they wish to continue reading the paper. If it's not applicable, put it aside. If it is applicable, then get inside, dig in through the details, and understand what's going on. Well, that's the idea behind a lot of methods. The name of the method and perhaps the parameter names helps condense the idea behind the method into a very brief headline description. It allows a programmer to know what's going to happen if he calls that method, but without necessarily understanding any of the details. One significant advantage to this is that the implementation inside the body of the method can change over time. Perhaps a faster or better algorithm is discovered, or additional processing needs to be done. That doesn't change the abstract idea of what the method name means. It only changes how it implements it. Now, this is a rule that is not apparent to beginning programmers. Clients, that is somebody's code who uses your code, should never depend on any implementation detail, only on the promise or contract that the method documents. That gives you as a programmer the flexibility to change the precise implementation, but never the function. Now, to do good abstraction, we have a couple approaches, the top-down design and the bottom-up. Top-down is mathematically called the deductive approach. We start with a firm concept, and because the idea or the concept is there, we can deduce or break it down into smaller pieces which must be true. They flow logically from it. The idea of a program, if it can be consolidated to a statement, can then be broken down into substatements with more detail that describe part of the overall problem. And that continues on and on until you can't really break the idea down further without writing the actual code. And that's at the lowest level. Architecting a building is an analogy. We have the idea first of a building, and from that, the architect develops a plan, and he can only go so far in the planning. At some point, he has to say, we have to stop planning and drawing pictures. We have to start constructing the building. Bottom up is exactly the opposite. We start at the bottom and work our way up. This is mathematically the inductive approach. We take building blocks and we begin to put them together until we wind up with a finished structure. Now, I wouldn't think constructing the building from bricks and boards and nails is a great idea without a plan. So neither top down nor bottom up ever tend to stand alone, but the bottom up is more of a construction concept. We take existing parts, put them together into something bigger and bigger, and we provide greater and greater function as those subparts are combined, and it works its way upward until we have finally solved a problem. The idea behind both concepts is to hide details or hide complexity so that the functional idea of the part, that is what it does, is used appropriately without any concern about its specific details of implementation. A building construction expert, a carpenter, bricklayer, plumber, sheet metal worker, they don't need to know the chemistry of how their parts work. They just depend on the fact they do. The general contractor doesn't need to keep track of the specific details that his subcontractors work with. He just needs to know that they are on track and doing what they should be doing towards the overall goal. Each one works at a certain level of abstraction. We as programmers do the same. When we input data from the keyboard or output it to the console, we don't really care about a lot of details that the hardware and certain layers of software have to work with. We just want the data. So that is an abstraction. System.in is an abstraction of the keyboard. System.out is an abstraction of the console. We just use them for what they promise, not worrying about the details. The idea of refinement works for both top down and bottom up. It is the idea of breaking a problem into smaller, more manageable parts. And this is at the heart of engineering. It is the management of complexity. No matter what problem you work with, it's best to break it down into small, manageable parts that work together, then work on each part. Small programs like labs for a class, however, actual development of real professional software is not. It is very complex and takes many programmers a long time to write. Each piece must be broken down to a manageable chunk, and that chunk worked on. The benefits of refinement include simpler construction of components and programs. We're not trying to solve every problem all at once, only specific problems. And in time, those pieces will work together to solve the bigger problem. We develop reusable parts for this and other programs. The libraries that Java provides is an example of this. We don't have to write the input and output routines every time we want to use them. We just simply use them. Easier comprehension at a functional level. That allows the minimum amount of details to be communicated to the point that a programmer will write a piece of code and he gets to understand very well what that piece does. He manages the complexity there, but it's at a functional level that it's used. Straightforward testing. Testing is very difficult to get right, and refinement allows code to be written in such a way that testing becomes easier. Therefore, the product becomes more predictable and stable because it can be verified. And finally, refinement allows smoother teamwork and cooperation between teams because as we're dealing with only small, manageable pieces of complexity, we together are more able to communicate and work well